Traveling to the 1750s, we find that scientists were putting different substances in flames and passing the resultant light through a prism. They found that the hot gases given off by the burning materials emit different colors of light or spectra. For example, ordinary table salt generated a bright yellow spectra. Furthermore, not all the colors of the rainbow appeared. There were dark gaps in the spectrum. In fact, for some materials, there were just a few patches of light. By the 1820s, they recognized that spectra provided an excellent way to detect and identify small quantities of an element in a powder that was put into a flame. Meanwhile, the white light of the sun was also being examined closely. And in 1802, it was discovered that the solar spectrum itself had tiny gaps. There were many thin, dark lines in the rainbow of colors. But the reason for spectral lines in the light and the relationship to each substance was a real mystery. Traveling forward from that era to a little over 100 years ago, scientists were examining the colors of light given off by solid heated objects. They discovered that these hot solids gave off continuous spectra, and that the overall color of the light revealed the temperature of the object. Now, this was important because scientists realized that this discovery made it possible to measure the temperature of an object from a distance. They could measure the temperature of the sun, for instance. During these discoveries, they also noticed that some of the objects absorbed light extremely well, almost perfectly in fact. They were called black bodies because they absorbed virtually all the light that was shown upon their surfaces. These same objects also radiated almost perfectly, and as noted before, the temperature of the black body object determined the distribution of colors or wavelengths in the emitted light. This curve shows how much light of each color is emitted by a cool object. As you can see, there isn't much light, and what light there is mostly lies out past the red end of the spectrum, in the infrared. The figure on the right will show the different colors added together as we progress. Right now, only red light is visible. This curve shows how much light of each color is emitted by a medium temperature object. And the most light is emitted in the orange, yellow, green wavelengths. So now we add orange, yellow, and green to our cauldron of light on the right. As you can see, the combination so far looks yellow. This third curve is for a really hot object. Lots of light, and with most of it being emitted toward the blue end of the spectrum. And as you can see, our cauldron now is pure white in the center where all the colors overlap. A heated black body follows this color path as the temperature rises. A good example of black body radiation is the heat inside a kiln. Inside the kiln, electromagnetic radiation, light and heat, exist in a form of standing waves. Waves that, like the vibration of a guitar string, are attached at both ends. The ends of the standing waves, like the ends of a guitar string, do not move. They are anchored to the sides of the kiln. And many, many waves exist with varying wavelengths of color. At low temperatures, the primary color inside the kiln is the infrared, and we cannot detect it with our naked eye. But as the temperature rises, the kiln begins to glow red, and as the temperature continues to rise, the dominant color changes to orange, then yellow, then bluish white. The distribution of energy in light shifts to shorter wavelengths as the temperature rises. But there was a problem. The scientists expected the distribution of emitted light to continue to the increase at wavelengths toward the ultraviolet end of the distribution. It didn't. Instead, there was less and less light given off as they were further and further into the ultraviolet. This was called the ultraviolet catastrophe. But it wasn't a catastrophe at all. It was the beginning of something remarkable. A truly great scientist named Max Planck soon figured out a way to explain the observation. He concluded that the energy contained in the standing waves inside the kiln did not and could not possess just any and all different amounts of energy. Instead, the quantity of energy these standing waves possess had to be limited to a few specific discrete values of energy for each color. A standing wave of blue light, for example, can have energy equal to 0 electron volts, or 3 electron volts, or 6 electron volts, or 9 electron volts, and so on. In general, energy equals any whole number, n, times Planck's constant, h, times the frequency of light, nu, which for blue light is any number times 3 electron volts. But notice, blue light standing waves cannot contain energy equal to 1 electron volt, or 2 electron volts, or 4 electron volts. Realizing that energy could have only discrete values was the beginning of quantum mechanics. The energy is said to be quantized, and n, from the equation above, is called a quantum number. Planck's conclusion that light energy is quantized was quickly used by Einstein to explain another puzzling phenomenon. It was known that shining a light upon a metal plate can release electrons from the plate. But the light has to have a certain wavelength before a single electron is released. We can shine brighter and brighter light on the plate forever, but if the color isn't right, the electrons stay home. Einstein concluded that the light striking the plate had to be coming in discrete bundles, and unless a single bundle had enough energy to free an electron from its captivity, it would remain trapped. And as Planck had suggested, the wavelength and frequency of the light was a measure of the amount of energy each bundle carried. So while blue light packets might be able to free an electron, red light packets could not, no matter how many red packets hit the plate. But wait a minute. That sounds awfully like light is a particle and not a wave. And there are mountains of data showing light behaving like a wave. Diffraction, refraction, interference. Which is it, a particle or a wave? It is both. These light packets are extremely tiny. Let's call them photons, from photos, the Greek word for light. And when you try to explain the behavior of things this small, you must resort to really unusual ideas. The ideas contained in quantum mechanics.